Okay, hello everyone. Welcome to a design review about chemistry. And we're actually reviewing something is not for version 13, it's for something after version 13. I believe this might be our first design review of something fundamentally for post version 13 that we've been working on for a while. All right, this is about molecular fingerprints. So it's basically an encoder for molecules.
Yes.
And why is this different from the net encoder technology? I mean, there's a feature detector story, isn't it?
Right. So it does. I mean, it is in a sense like featurizing a molecule, but it's and we did meet after the last time we discussed this with the machine learning group, and it is kind of in a some form hooked up to feature extraction. There's a few named extractors there.
Okay.
But
So why isn't it just a feature extractor?
Right, because so in general, like the people who are interested in fingerprints are going to want to be able to tweak a lot more parameters than are normally available for in a feature extractor. So
Is that true? I mean, don't feature extractors also have tweakable parameters?
I don't know the extent to which those not in not in any way, not to the extent that these do. I don't know if there are sub options for these.
Do we have anybody from the machine learning group who could speak to that?
No. So I did not with us today. So when I met with them, they were of the opinion that I mean the.
Can we find somebody? Can somebody find somebody? Is anybody available?
Yeah. Do you want me to just ask Shadi for somebody?
Yes.
Okay.
To suggest somebody. Okay, go ahead.
Right. It's that so with these feature extractors, these named feature extractors, they wanted something that was really kind of turnkey, that was would do what the user will expect it to, and will just kind of fit in there and work. And in general, from what I've read and looking at I mean, just as an observer, machine learning and chemistry is not. It's not nearly as mature as it is for video or audio or images.
I know, but it's going the exact same direction.
Right, but it's so at the moment when various people do machine learning, they write papers about it. They basically have to at each time write their own encoder, because the different features that get encoded into the bit vector are different for each purpose you need.
I understand. So there's not just one feature detector. I mean, just like that's why, I mean, in the case of machine learning, we learn a feature detector. These are named ones, but we can also learn one. Okay, right. So let's just take a look at, so you have, if I look at one of these, this is just a numeric array.
Right. It's just, and if you normaled it, it would be ones and zeros.
Okay.
And so, and we had previously looked at the bit vector data structure as a return type, but it just doesn't. They're not as built into the system as the numeric array. And so, I mean, what's nice is with that numeric array, you can feed it into most distance functions, most other functions throughout the kernel, and they'll understand what to do with it.
Okay. You know what? This is not a properly integrated design. I mean, this is something where, okay, let's look at a few more of these things. I see. So you can make a distance matrix between molecules from this, yes?
Right, if you supply it with a dissimilarity.
No, well, obviously this is not going to make it. This is a string option for a.
Right. So I mean, so I really want to get your opinion on which way to go with these before I code them all up.
What is molecule dissimilarity? Is that something that's going to be added to our collection of dissimilarity functions?
Yes, I think I believe so.
Right, I mean, that's the plan. And by the way, what's the status of our graph encoders for neural nets? Do you understand the question? I mean, we're doing, right, which are clearly closely related to encoders for, I notice someone on our live stream is making the same comment, that it's a, and I don't know whether those again have many parameters. I think that they do. So I think we may have already solved the problem of representing a feature extractor with parameters. Ethan is saying the graph encoders suck. Our graph encoders or graph encoders in general?
So if we've solved how to make a feature extractor and with usable, like documented parameters that you pass in, that wasn't expressed to me when I met with.
Okay, well, so you got the wrong, if I might say so, we have the wrong people in this meeting, because we clearly need, you're asking me a bunch of details about how feature extraction works. I thought there was a separate documentation page. There isn't. So I'm a little bit surprised by that. I thought there was a separate documentation page for each of these feature extractor types. Okay. And one of them I would expect to be, your different kinds of molecular fingerprints. Because I mean, again, here, if I take one of these, notice that this gives a feature extraction function. I think you can get the actual vectors out. Okay, you know what? We need whoever is working on the graph encoders and so on, because they're clearly going to be deeply related to this. And what roughly is the algorithmic approach taken by these molecular fingerprint things? They're presumably doing some kind of graph encoding. Is that true?
Right. So you find some type of substructure within the molecule, be it a pair of atoms or a group of atoms, and then you take those atoms plus the information about them, and you hash that to some integer.
Mm-hmm.
And then either you keep track of that integer and how many times that substructure shows up, or you fold that integer down to a number between 0 and 2048, and you set that bit to 1.
Sorry, what? Fold what number? Sorry, what?
So let's see. So you look through the molecule and you find all the different substructures. You take that substructure and you hash it to a 64-bit integer.
That's random. Okay.
And then if you want to represent that as a finite bit vector, you then take that 64-bit integer and they call it folding it down, but I mean essentially hash it down.
It's flattened. Is it flattened? It's just flattened. So it's just you get a list of those things and you flatten the list. Is that right?
Well, no. For each individual substructure, it's originally hashed to, as Jason said, an integer. That is a very large space. That all of those different integers, and in chemistry, they have frequently folded them down into 0 to 247. And then call that a bit vector that they would then use in a dissimilarity measure. That's the history.
Okay, so basically what happened, well, what you're saying is, if you just took your molecule and you took its smile string and you hashed it, you would have something which has no chemical, no reason to make nearby molecules be nearby. Okay, exactly. But what you're doing is, you're saying, take the graph, look at its graph substructure, and take each lump of substructure and do a random hash on that lump of substructure, on the grounds that if two molecules are the same, they have lumps of substructure that are identical, as in they'll have the same hash.
Basically, that's it. And it's the degree of overlap of those hashes between the two molecules that's the similarity or the distance.
Well, but each substructure, each hash is just completely random in hash space. So the whole point is, what you're saying is the molecule can be decomposed into subgraphs. Each one of those subgraphs is subgraph number 312 or something. And it's just, and it has no relation to subgraph 311. But
that's
what
true.
You've got is basically you're saying which are the subgraphs that occur in this molecule. It's one way to do it would be to say, if you can do it at a more human level, you would say this molecule has I'm trying to learn chemistry, aromatic ring or something. This molecule has a such and such, a phenyl group or something. I don't know what I'm talking about, but these named sub pieces of molecules.
Functional groups would be the term.
Say that again, John?
Functional groups. So you're trying to match functional groups between different sets of molecules.
And basically a skeleton as well. But
yes, skeletons.
Whether or not they hash, two similar things that we might think of similarly when we look at it in a graph theoretical sense, whether or not they hash to nearby integers has been irrelevant for chemists.
Hopeless, yeah. Hopeless, right?
Well, actually, no. It's a label of something that's in the molecule, and if two molecules both have that same label, they both have that subpart, and they're similar in that respect. And it's the aggregate of all those similarities that gives the overall molecular similarity.
I get it. But I mean, if you have two things that have the same functional groups, but they're arranged in a different way, you would have similar hashes, but the molecules would be different molecules. Is that a true statement?
Yes, because other things would be different between them as well, besides those two specific subgroups.
Yeah, but in the construction of your fingerprint for the molecule, how does the other graph structure, independent of the subgraphs, how does that affect the fingerprint?
It will contribute other substructures to it.
So the substructures, they overlap, right?
I see. So you're decomposing it, and the point is that, okay, I get it. So if I was doing that for a vector of integers, for example, what you'd be saying is, I mean, it would be as simple as taking some random vector of integers, for example. The analog of what you're talking about is, let's say I say random integer, I don't know, and then what I would say is just partition that, 5, 1, and then I would hash each of those subgroups. Is that right?
Or be more subspaces.
What do you mean by subspaces? This is, I mean, I just...
You enforced an order.
Well...
Oh, I see. Subsets. You're saying arbitrary subsets.
Okay.
Not necessarily, though.
I was thinking in vector space, subspaces.
So, but the way that you partition that, you only group the things that are near each other, so you're getting like linear substructures in that linear list, right?
Yeah. Okay, fine. But all right, so then...
And so there are different algorithms for how to generate those substructures. Do you look at pairs? Do you look at paths? Do you use a circular radius to define a substructure?
I get it. I can see how that would work. Okay.
And so let's see, I understand that like all the different parameters in that is not perfectly well integrated with the rest of the system. And so that's why I put forth the idea that the fingerprints could go in the WFR if
well, I don't know. I don't think that should be necessary. I think that they can be... Okay, this thing here is doing a search. When you say CNS agents, that's... So, okay, so this is a known list, and this is really doing the same thing that Nearest does. Is that correct?
Yes.
Okay, and why isn't this just a distance function?
Let's see. So when doing molecule similarity, you need both how to what fingerprint types to make, and then how to compare them.
So that's like a feature. Okay, so this is, so presumably when we make a feature space plot of molecules, we would be using, if I'm not mistaken, these fingerprint feature vectors, yes, to make the feature space plot, and then dimension reducing them.
Yes. And so essentially what I want, right now you can say feature extractor goes to, and then give a string or a different string. And I'd like there to be the possibility of a molecule fingerprint function, which you've specified all the different parameters that you like.
Although we could also imagine something, and this is why we need somebody from the machine learning group, something where you give the name of feature extractor, or you have some wrapper that represents these feature extractors together with a whole giant association of attributes used by the feature extractor.
Stephen, I don't think the odds are good of getting someone from the machine learning group.
Okay, well, I don't think this, then I don't think the odds are good of resolving this in this meeting.
Okay.
Okay. But I mean, just to understand this better, I think what you're saying seems fine. I mean, except that I just don't think, I think this is exactly a feature extraction function, and I think it should be treated the same way. Why is this any different? I mean, this is, it's exactly the same type of thing. Right? What's the difference between this and feature extraction function?
I don't know anything about the latter.
Okay, well, it's fine, but that's you know, that's what having an integrated design is about. Is that I'm telling you, it's the same thing, right? And that's what you should be using. And maybe this will push to get more detail and more documentation of how these feature extractors work. Ethan on our live stream has been talking about how bad our graph feature extractors are. So it sounds like there's a feature extractor gap here. And
I wasn't aware that we had implemented that.
Yeah, well, okay. So there's been a lack of communication here. So let's solve that. Okay. Okay. Is that other stuff that needs to be? So you've got a bunch of different parameters effectively for your feature extractors here, like the substructure keys, molecule substructure keys is probably the name of that feature extractor, and then it has various kinds of parameters associated with it. Yes.
Yes. Although, I mean, so in that particular case, you are supplying a literal list of molecule patterns, and then it is checking for them. So that substructure patterns.
Where's the list of patterns?
So here, entity value, element, atomic symbols. So basically, so in this case, it's just checking. It's essentially getting the molecular formula. It's a toy example.
Okay. So this is, by substructure patterns, you mean that is the function applied to substructures, or no? That is the function that is determining what the quote substructure of the given molecule is.
Right. So you could put in your own patterns there.
But what's it going to be applied to? I mean, that particular, it's applied to the whole molecule object, or what?
Right. So you do. So it essentially. So you would put a list of molecule patterns in that where you have it highlighted, and then the fingerprint would have 0 or 1 depending on whether the molecule had that substructure.
Okay. Fine. I mean, so what you're saying is, okay, so there's a language. So you're basically saying these fingerprints work by identifying substructures, and then your output type there is count vector. Okay. So you're saying you break the molecule down into these substructures. Each substructure has a code, hash code or otherwise, assigned to it. Then you have a combiner function that takes those individual codes and packages them together into the final output. Is that right?
Yes, that's very succinct.
That's a good summary.
Okay. All right. So then what? Okay. So these are the ways that you are selecting which substructures you're going to pick up from the graph. Is that right?
Right.
Okay. So, I mean, I just don't think this is terribly complicated. I think that this seems like it fits well into the rubric of feature extractors, but the feature extractors are going to need some extra parameters. Hopefully you are going to have a bunch of named molecular fingerprints, which are what people typically want.
I do have one question though about the features that ultimately get extracted. Generally, the chemists have dealt with vectors of zeros and ones or counts, and the machine learning features tend to end up as arrays that can go into some kind of neural net generally. So is there a way we can handle both?
Sorry, say that again. Could you just repeat for a second?
Okay. Traditionally in chemistry, the features end up becoming a list of bits, zeros and ones, presence, absence, or a vector of frequencies or counts, how many times each one occurs. And in the feature extractors for machine learning that we have, they ultimately end up as an array so it can go into a neural net. And we don't want to necessarily, shoehorn what has traditionally been vectors.
These are just vectors too. That's what neural nets eat.
Right, but sometimes we want to return this association with counts.
Which association?
Like, so if you go down to one little bit there, so that we made that when we made the fingerprinter of the substructure keys, what its output is like that H goes to 6, C goes to 6. So it tells you these substruct not only did it set bits, but it also
has an explainable version of what the feature extractor is.
Yeah.
Okay, well, that's exactly what people want to do in machine learning as well. They want explainable feature vectors. So I don't know what we're doing exactly for explainable feature vectors, but this is probably the same kind of thing. That is, in that particular case, what one's often doing is saying, which features were the more important in determining this result. And that's a little different from what you have here, but it's the same structural problem, I think. Right. So, yeah, well, look, I think the main point here is let's get what am I trying to say? Let's.
So should I meet with Etienne and Tim?
Well,
again,
not
and
Etienne,
then come back?
Julio.
Okay, Julio and
Jerome.
Okay.
Yeah, Jason, please include me in that conversation as well. I have a lot of experience with these things.
All right, and then my bottom line is it's possible that there should be a separate molecular fingerprint function, but it's also got to interoperate with all the machine learning stuff, because then it plugs into feature space plot and all these kinds of things, dimension reduce, all these types of things that we would expect to work. The question of how the human readable, that's the only thing that I understand, as I understand it, that you want that is not obviously available in feature extraction is a human readable version of what the feature vector is. Is that correct?
Yes.
Yeah.
Well, so to a degree, I also really like that let's see, to a chemist, they don't the people who are interested in these might not think feature extractor when they want to get some molecule fingerprints. Like having the name be molecule fingerprint would have a certain.
Well, we can consider that, but let's make sure that we understand that. I don't know. We have a few other special case feature encoders, I think. I think there are ones with color, which are, like we have a color nearest and so on. That isn't just, I think we do at least, that isn't just the generic nearest. Maybe we don't. I think we do. Because I think it has, no, we don't. Maybe it's just
color distance.
Oh, okay, that's what I'm thinking of. Right, because that's a special distance. And a molecular distance is, again, something, presumably we need, didn't we already have such a thing? Molecular distance, molecular dissimilarity, is that not already a function?
It is not. So I proposed this a while ago, and I have let's see, a fingerprint similarity function in the repository.
Okay, fine. Okay, maybe that's where I'm thinking of it from. Look, I think it should be built in. Whether there is a molecule fingerprint function name, let's find out how well this maps into the feature extraction world and take it from there. Is there anything else we need to cover right now, right here?
No, that's it.
Can you, just for my, a little bit of the roadmap of some of the other things that we'll be seeing in chemistry in the near future? What's ever happened to like electronic structure computations and so on?
Let's see.
The next thing you want to do is the chemical reactions, the reaction templates, right?
Right. So we have a reaction, a template reaction that is like an operator that can affect transformations, and so it basically transforms graph patterns from one side to the other.
Okay, so it's that particular one. I'm going to say right now, we obviously have done tons of stuff on graph rewriting in the physics project. That has not yet been imported into the graph framework. It's going to be. Let's make sure that we have something which is compatible between these chemistry graphs, graph theory graphs, and the stuff that has been coming in from the physics project and so on. Because I think your chemical reaction, and by the way, I think these graphs are going to be closely related to these two-way pattern things that are also relevant for theorem proving, etc. I think it's all the same type of thing. And we would like to have a nice coherent design for all of that stuff. But you should design what you need for the chemistry thing, but expect that, you're going to specify molecules with pattern variables, I assume. That's what you already have, right? They're random R's that are pattern variables in molecules, correct?
Yeah.
With smarts, using smart, yes.
Right. And then what's going to happen is you're going to say this graph with this form has this, wildcard blank thing in some place. Now you can, put anything in there, and that's what represents the reaction. Is that correct?
More or less, yeah.
So you define patterns on the left and like identify what happens to them on the right side.
Conditions.
Yeah, it is the graph rewriting, and what's not specified in the pattern for the reaction is that blank for all the rest of the graph for all the rest of the molecule. And sometimes we do specify that explicitly in the reaction pattern.
Well,
it's
okay,
basically
so
the graph rewriting, yes.
Okay, so hold on. So an expression rewriting /dot, as opposed replace takes the whole expression and does what it does with it. Replace all, recurses in the expression and can take a subpart of the expression and transform that.
Yes.
So you're saying the default for molecules is the second case. Is that right?
Yes. Because basically that's what happens in the flask.
Yeah, right. Replace all is actually the best analogy for this, because if you have two identical functional groups at different parts of the molecule, they're still supposed to react the same way to a given reagent. So yeah, replace /dot is a good analogy for this.
But I don't necessarily know about that. So if you have two functional groups like at different ends of a molecule, and you have a reaction that transforms a functional group to a different form, then you could have two different products when you apply that reaction.
Yes, it could go to the left, it could go to the right, and it could also
it's more
do
like
both
replace
of them.
list in that
Yeah,
case.
that too.
If you apply it twice,
guys,
it would be like it would replace both.
This is in the category of everything, all simple things are invented many times. This is exactly these multi-way graphs. That's why, in fact, there's a group we've been interacting with in France that have built a bunch of things that are based on category theory ideas and so on, that are chemical reaction networks, and trying to understand the correspondence of those to graph rewriting that we've done for physics project and so on. But if I look at sometime in the past, one of you got me to buy this book about name reactions, and it just has this catalog. And I have another book, some E.J. Corey book about logic of chemical synthesis, which is a great big list of, it's a great big list of reactions. And so, looking through there, my assumption is that each of those reactions are going to turn into a graph pattern.
Essentially, that's my view of the world as well.
Okay. And then what's going to happen is those, in terms of our chemical reaction functions, there will be some essentially multi-way graph that says these are the different possible things that could happen given this transformation rule to this particular molecule. And presumably each one will have a weighting that's determined by all kinds of thermodynamic features and so on. That a fair?
That's a possibility, yes.
Or in practical terms, you may get a higher yield of one particular product than the other.
Yeah,
depending on reaction conditions. Yeah, it could be thermodynamically controlled or kinetically controlled.
Kinetically controlled, yeah.
But by kinetically controlled, do you mean the molecule is a certain shape and you can't get the thing into it? You can't sort of kinetically move the one molecule to fit with the other molecule, or what?
Kinetically controlled, I think, is more having to do with how many things you've got reacting, whereas thermodynamically controlled, it'll go to the lowest energy one. It's a dynamic equilibrium. And even though, A is formed first, it could rearrange to the other product B eventually.
Okay.
Depending on the reaction.
Well, you guys know that I'm trying to understand some of the stuff about foundations of chemistry for my strange purposes of trying to apply physics project ideas, and particularly of relevance, I think, is this kind of microstructure of reactions. That is not just asking what is the total amount of this product that's produced, but asking what's the detailed causal graph of which molecules interact with which other molecules. It's kind of the below thermodynamics version of what's happening. I don't know whether that resonates with anything. I mean, when you think about what you're describing in terms of one functional group doing this and then the thing rearranges and so on, that's one level of description is everything works according to thermodynamics. But another level of description is individual molecules have individual transformations that happen on them, and it's only in the aggregate that you get thermodynamic behavior.
Yeah, I think so.
Sure. Yeah, you could say that.
So actually, okay, this is my chemistry moment, and then we have to wrap up here. My chemistry moment is I was trying to understand these things like autocatalytic sets. Do you guys understand those?
I'm not familiar with them by that term.
No, I don't know that term.
Okay, they're studied particularly by people who are interested in origin of life kinds of things, and they're basically sort of molecular cycles that have some kind of self-amplification property. Okay, but this whole question about looking at the detailed kind of causal graph or the detailed sort of evolution graph of what molecule gives what molecule, et cetera, et cetera, et cetera. How would that be? I mean, in traditional sort of chemistry, one is mostly concerned with what will ultimately turn into ODEs that represent the concentration of different chemicals, correct?
Well, that's one thing. Some people are interested in that. Others are just interested in being able to make a particular chemical compound.
Right.
In good yield.
Yeah, right. Yeah. To find a particular path through this multi-ray graph that gives that particular result.
Yes. And others are interested in stability of molecules and their structure, and then or the kinetics of the formation.
This is irrelevant, but Sandra on our live stream is asking about that distance function, and I have no idea why that's still experimental. It's a different group, but somebody should take that and ask that question. I have no idea why that hasn't been promoted to the system context.
Okay, we'll pass it along.
All right, I should probably disappear here, but all right, this was the beginning of a new development cycle, and I think this, we talked through this and connect with the machine learning group, and there are various comments on the live stream saying we should get a version of AlphaFold in or something like it in the neural net repository. Yes, I agree. And it would be nice to get, although it'd be nice to get a version, one of the faster versions of that, so that it's actually something that's realistic for people to do in something more like real time, at least to an approximation. All right, but I think I have to run off here. So thanks a lot, guys. Thanks to folks on the live stream, and see you later.